Yeah, our next presentation is from Guru Prasad of Intel. Is it? Last one. So please vote for the last presentation as well as all the presentation. Whatever if you have missed, please vote now because after I think 5:30, 5:30 they will close the assessment and start using that data for deciding the best paper and the second best paper. So please enter your voting for different papers. Okay, so Guru Prasad is working at Intel. He is particularly from the design side. He is an IP designer. He holds a overall industry experience of 13 plus years, and he's working as a design lead for debug IPs at Intel since last 5 years. Has expertise in designing physical layer IPs and subsystems in wireless communication domain. He holds US patent in forward error correction domain. Give a round of applause for the Guru Prasad. Thank you.
Thank you, Girish. Good evening, everyone. Myself, Guru Prasad. So I'm working at Intel in IP design team. Basically, we handle multiple debug IPs. Okay, I've been at Intel from past 5 years. Firstly, I would like to thank DVCon team for giving us this wonderful opportunity. And at the same time, I thank my teammates, Vishnu and Mansi. Okay. So here we start. So so we saw, a lot of verification teams, emphasizing on doing the left shift in the verification, process and finding critical bugs early in the design cycle. Okay. And of course we know, why do we really need to have catch the critical bugs early, and why do we have to really left shift? Okay. So as a designer, how can I aid them? Okay. How can I help my verification team so that they spend their quality time in finding the meaningful bugs? Okay. So how can I help improve my design apart from the usual static checks that I have at my disposal? Okay. So that is the focus of this presentation. Okay. Yeah. So basically the introduction and overview and the type of design checks that we do, okay, before we hand it over to the verification team. And basically, this presentation is focuses mainly on the auto-formal checks. Okay, so overall, generic tool flow methodology and what are the different auto-formal checks that we employ, okay, to qualify my design. And so then that is one part of the design, and I will cover the case studies, based on our learnings. So basically, we are, we have been initiated to the formals very early. So we are, still, in a learning phase of formal, but still, how we can make best use of these auto-formal checks. So that I will cover through some of the case studies. So then we'll discuss the results and the conclusion. Okay. Okay. Yeah. So we have already linked, like CDC and all, DFT and all those static checks. Okay, and we also qualify our designs with sanity checks. So why auto-formal? Okay, so we combine, this structural checks along with this auto-formal checks, where with the least effort of the designer, the properties are extracted. Okay. So so basically applying auto-formal checks, it helps to find the any design functional issues very early in the design cycle. Like as soon as you are done with your RTL design, so basically you run it through the lint and you check, you make sure that it is synthesizable. You do all sorts of structural checks, and the CDC design is correct. Okay. So then this gives you a means to find the functional issues as well, dynamic issues as well. Okay. So so these issues, some of them could be very trivial issues, but this tool can this auto extraction of the properties can really find the critical corner case bug which can potentially be missed in the dynamic simulation as well. Okay, yeah, and the ease of setup. Okay, so this is the biggest takeaway, because as a designer, I cannot spend a lot of cycles on setting up the tool, and basically to repeat what verification team could have done. Okay, so in very less time I can set it up, and I see that basic functionality is working. Okay, yeah. So yeah, along with doing these structural checks and DFT checks, we also do these auto formal checks, which are uh, basically it detects dead codes, FSM reachability, and FSM deadlock and live lock. Okay, so and it can detect arithmetic overflows. Okay, we will discuss in detail about these things. Okay. Okay, so yeah, so what is the tool flow methodology of this? Basically, my design needs to be synthesizable. That is the first prerequisite. So anyway, so through our lint and CDC, we make sure our design is synthesizable. Okay, so once the synthesizable design is fed, so the design is analyzed. Okay, and that auto form. I mean, the on analyzing the design, the properties are extracted from the design. Okay. So yeah, I mean the tool will generate the properties for you. Okay. So then we can prove those properties. Okay. So once we prove those, basically, I mean it's a brute force kind of thing. Whatever possible scenarios are there, it will try to extract that. Okay. So but as a designer, I know what are valid scenarios and what are not. So for that, I mean to restrict the properties, I write assumptions. Okay. So these are similar ones. Like if you are familiar with the formal flow, so we write assumptions so that we can restrict the tool behavior. Okay. So yeah, so then after that I rerun that and analyze the results, and then I debug. If it is an RTL issue, then I fix it and repeat the process. Okay, even though I mean update the assumption, then I again prove the properties again. So again to check if there are any issues with the design. Okay, this is the flow. Yeah. So what all auto formal checks are done? So basically signal deadlock checks. Okay. So this is something like if signal is not toggling. Okay. So then the case checks whether the case is traversing to default or not. Whether there are any deadlocks in the FSM. Okay. And there are any dead codes. Okay. So just to I mean emphasize a little bit on this, right? So this deadlock checks and dead code checks, right? So when we do coverage analysis, almost at the end, I mean, after completing all our verification cycles, regression, we do coverage analysis. Okay, so then we see what part of the code is covered and what is, I mean, not really. I mean, it's covered and what that part of the code is not being exercised. Okay, so it happens generally in a very late stage of the design cycle. But with this auto formal checks, right? So it can happen soon after my RTL completion. So it's a huge left shift, and this code cleanup, I mean, it really saves time and like verification cycles in overall my design cycle. Okay. Yeah. So why we started employing this auto formal checks? So basically, we wanted to like test it on our legacy IP and prove the concept, and later use the same auto formal checks for all our new features. Okay. Yeah. So then I mean, how to prove that? So we knew there were some issues, so we prove that that auto formal checks really catches that issue, and that then I mean we know that a tool is something really working. It's not throwing some false violations. Okay. Yeah. Then fix that RTL and test that so that that whatever violations were caught, so those are fixed. So basically, this was proof of concept. So once that was done, so then the plan was to use it in for all our new design features. Okay. So what were the challenges? So yeah, if you are, I mean, aware of the formal world, right? So the convergence issues. So we also faced convergence issues because as we were directly using it on our legacy IP, which is of multi-million gates. So we really had the tool running for days. Okay. Yeah. Then because of that huge runtime, the huge memory requirement, and runs being hung and being killed. Okay. Yeah. So so basically it extracts all the properties from big design, right? So it's a huge list of properties. So when the tool is running all of them at the same time, so then we had to, overcome this challenge. So as a designer, I'm not, afford to, let the tool run for days and then show me the result, right? I want something quick and dirty. Okay. Okay, so let's cover some case studies. So yeah, how we could make best use of the formal. So we had a this clock management feature. So as part of our low power initiative, so we had to design a control structure which involved an FSM. Okay, so yeah, we ran the FSM through auto formal checks. So, but we wanted some stimulus where we have the gated clock. Okay, so we explored and we saw that that uh, there was no way that we get the gated clock through the auto formal. So we created a like a wrapper kind of thing where we modeled a gated clock and again constrained the that enable pin. So the way so that we can produce various clock gating scenarios. Okay, so that it creates a lot of corner case scenario for my new feature. Okay, so yeah, so that could unearth a lot of issues related to the my architecture definitions. Okay, so that helped to streamline the architectural definitions, which I otherwise would have been caught very late in the design cycle. Okay, when the real verification cycle starts. Okay, so yeah, that again that led to architectural changes and design changes. So we repeated the cycles. Okay, yeah, so in this process we faced a lot of challenges like there were false violations. Yeah, and we'll just address how we how we address that. Yeah, so finally we could prove all the that design, all the tests passing for the design. So yeah, so we could achieve 0 bugs for this feature. Okay, with the formal auto formal checks. Okay, so when we passed this design on to the verification team, so it was there were no bugs found on this, and we deployed this IP into various products. Okay. Yeah, so yeah, we faced a lot of false violations. So basically, we had to educate the tool. Yeah, someone who is new to formal, so the formal throws huge number of violations initially. Okay, so we really have to analyze and see whether that is valid or not. Okay, so yeah, so the tool was thinking that that we had to educate the tool that some of the signals toggle at least once during the simulation. So we had to add all such assumptions, and then we could start seeing the meaningful results. Okay, yeah, there was another example that I would like to discuss. So basically, this was the legacy design. Okay, so it was deployed in multiple products, but we just wanted to test the formal application of formal auto formal checks on this design. Okay. Yeah, so when we ran our auto formal checks on this, so it could unearth one very corner case scenario, which was very difficult to create in the dynamic simulations. Okay, so so it took us multiple debug cycles to really prove that it's a valid scenario. Okay, and also another usefulness of this formal checks was whatever RTL fix we came up with. So since it was not caught with the dynamic simulations, right? So it would have taken weeks to find a proper test case to create that scenario and test that scenario. So we just did the fix and we just tested that fix in matter of days basically, which otherwise would have taken weeks. Okay, and as this was already deployed in various products, so we had to come up with a software workaround. Okay, so that software workaround itself was that also was verified using the auto formal checks in a matter of days. Okay, so yeah, this we could prove that with confidence we could sign off that this workaround is fine and it works. Okay. Yeah. So again here, since it was a big design, so we faced a lot of issues. So tool generated that whatever that assertion you see in the first line, right? So it sees whether the FSM state is stuck in that forever. Okay. So it was taking days of time to converge this uh, property. Okay. So here we just, I mean, converted it into safety assertion. So we, as a designer, I know that if it is stuck into this state for 100 cycles, then that is enough to prove that it is hung. Okay. So yeah, so that days of, I mean, the time that was, the tool was taking, that was reduced to hours, and we could prove that the hang is real. Yeah. So yeah, so this is just the, I mean, representation of that. And here, I mean, we could test that all the RTL fixes and software work around with the auto formal checks. Okay, yeah. So, I mean, it's been, I mean, very recent. So since we are using this, so we could apply it over 2 or 3 features, and we are seeing very, positive results. So that which I want to present here. So yeah, it also, I mean, we also did some structural checks. Okay. Yeah, dead code checks. Okay, signal deadlock checks, and the FSM deadlock checks. Okay. So all these were, detected at very early stage in the design cycle. Okay. So which enabled the verification team to, verify the design for the real issues. Okay, not for some cleanup kind of thing. Okay. And yeah, I mean, we really didn't have to wait for the sanity test to be provided. Okay. Yeah, since I mean the verification environment and design, that code development happens at the same time, right? So we didn't really have to wait for the val to complete the environment and give the sanity test. So we could be self-reliant with this. Okay. Yeah. Conclusions. I mean, it really equips the designer with the ammunition so that we can find real issues very early. Okay, yeah, and we are decoupled from the val team, so we have our own means to do the functional checks. Okay, and another advantage of this is we along with the auto formal checks, right? So if we combine this auto formal checks with the formal unit level tests, right? So I mean, it can be self sufficient to deliver the design. And another thing is that whatever assumptions and whatever pre-work you do for auto-formal checks, right, that can be directly reused to uh, uh, unit level formal verification as well. And our approach here was basically to do the module level test first and extend it to the IP and the subsystem. So whatever work you do for the module level test, whatever assumptions you write, whatever constraints you create, okay, so that can be directly reused at the IP or subsystem level. Okay, yeah. So yeah, there are challenges. There are huge runtime. So we could address some of them through concurrent, the divide and conquer method. Okay. So we were running only whatever was required for us. Okay. And also it the tool extracts a lot of properties. So I may not be requiring all the properties to be run. So whatever is my interest, so I'll just only test those properties. So I'll get the result very fast. Okay. So through such method, ways we could address huge runtime and convergence issues. Okay. Yeah. So yeah. Basically, with all these limitations, still we found that the auto formal checks really produce great results and really help to enhance the quality of the design. Okay. And yeah. So zero bug is the quest of the designer, right? So yeah. So there are various ways that we try, so that we really hit that zero bug thing. So this one, auto formal checks it really equips the designer in that process. Okay, so yeah, that's all. Question.
Thanks, Guru Prasad. It is really heartening to see design engineer adopting the formal. This is what all of us DV community wants to see, formal being used by designers so that we can do more complicated verification using formal. Thanks for sharing your experience. Any questions for Guru Prasad?
Hi, Guru.
Hi.
Do you have any automation like a script for analyzing the failures or errors from run to run?
Okay.
So
So
there-
you.
Yeah, so there can be a lot of warnings regarding the functional lint checks. or
Okay.
failures.
Okay.
So do you have any automation like there can be potential live logs, maybe not the true deadlocks. So do you have any like automation to improve the like
Okay.
debugging?
So yeah, we don't have any automation for that. So basically, I mean, we come up with the constraints, okay? So which can be reused at various hierarchies, okay? So but for those tests itself, we don't have any automation for that. So basically, the tool does the job for us.
Any other question? Thank you. So we have a question from Judge.
Yeah, hi Guru.
Hi.
So I wanted to know that you talked about false violations coming during the live logs and you had to put in fairness constraints. How long and tedious was that process in your experience and how much time it took to arrive at a point where you were able to, you showed that the properties got proved
Yes.
ultimately.
Yes.
So yeah, what was the experience there?
Okay, yeah. So basically, yeah, initially, I mean, it took a lot of time for us, okay, because since we were new to the formal, right? So yeah, we had to interact with the EDA vendors and we had to interact with our internal formal team at Intel. So yeah, so then for our first design, it took, definitely, I mean, significant amount of time for us to come up with those assertions. So once we were proficient with that, so our next designs, we were, I mean, able to come up with the assumptions before we could run that tool.
Okay, so after that it was kind of reusable.
Yes,
and
yes.
Okay.
Yeah.
Thank you.
Yeah. So and whatever learning we have with the, I mean, with our initial design, right, we can carry it forward for the next, so that, I mean, we save a lot of time.
Thank you.
Thank you.
I have a question.
Hi.
So you talked about huge runtime you have faced, right? So as a designer, you know in and out about your design. So do you put any kind of abstraction? Say we DV engineers put a lot of abstraction techniques for easy convergence and everything.
Okay.
So when you analyze your design, you know where things are getting blocked, or like say you have huge counters, and also in the design phase itself, do you put any kind of optimization? Say if you pass an option like some definition, fast mode or something,
Okay.
which will help in a better convergence or something. Do you suggest something like that while designing, or?
Okay. So basically we had, we followed divide and conquer method. So basically it involves, black boxing some of the designs which, are not part of the, cone of influence of my design. Okay. So then another thing was, there is a way to, disable other properties and run only the properties that I am interested in. Okay, so I know I want to prove that property, so I run only that property. So that was, one of the ways for me to reduce the time. Yeah.
Thank you.
Yeah, any other question? Okay. Thanks, Guru Prasad.
Yeah,
May I
thank you.
request Robuna to hand over the certificate?
Vishnu?
These certificates? Yeah. Yeah, you can give all of them.
Listen to them, the children of the night. What sweet music they make.
It's okay, it's okay, it's okay. Come. Thank you.
Thank you.
Show this. Thank you. Thank you. Thank you, sir.